Good morning to all of you. Good morning. Good morning. So are there any questions, doubts? Anybody has any question, any doubt on whatever we have discussed so far? Okay, so if there are no questions, so let me start. So today I'm actually just want to mention a few things about finite deformation, what we have discussed already. So, and then I will start contact mechanics. So last class we were talking about hyperelasticity. Okay. Is my screen visible?
Yes, sir.
Okay. So last class I was talking about hyperelasticity. So we have discussed the basic concepts. So one problem with when you do the finite element formulation, so for many other materials are actually nearly these polymers, many other polymers, biological tissues, etc. are nearly incompressible. So there is a problem what is known as volumetric locking. So what it states is that for near incompressible or incompressible or nearly incompressible materials. So that means for these materials J, the determinant of deformation gradient J will be nearly 1. So now we have for incompressible or nearly incompressible materials full integration elements. So we integrate all the stiffness terms using full integration as required based on the polynomial. So full integration elements under predict the displacement. So this is known as volumetric locking. So this is similar to what we have actually discussed for the shear locking in plate bending elements. So it is somewhat similar. So this is known as volumetric locking. So now how do we eliminate this? So for that there are a couple of methods. I think I'm just only going to briefly mention. I am not going into details of those. So to eliminate volumetric locking, we can either do a couple of things. So one is known as reduced integration. Reduced integration for volumetric part. So now if you remember, we have decomposed the strain energy density function into distensional part and dilatational part, that is volumetric part. So in the stiffness equations, element level Gaussian equation, incremental form, whatever terms are coming due to from the volumetric part of the strain energy density, they are under they are integrated using less number of gas modes. So reduce integration for volumetric. So typically, suppose if we have 8-noded brick element, so full integration rule will be, for this full integration would be, this is a 3D element, 8-noded brick element is a 3D element. So for this full integration, maybe 2 by 2 by 2 integration rule. So for volumetric part, you will use 1 by 1 by 1. So that is just 1 point integration for volumetric part, and this will take care of the volumetric locking. So that is one way. Now if you have 20 noded brick element, you might want to, full integration might be 3 by 3 by 3 or 4 by 4 by 4, and then you use 2 by 2 by 2 integration for the volumetric part, so it eliminates the volumetric locking. Sometimes there can be spurious modes, so to overcome that, you may also, in addition, there may be, there may be need for hourglass control. So we add an additional stabilizing matrix, so to control the hourglass modes if they are there. And so this is the reduced integration kind of thing. And there are another one is modified interpolation for J. So now in place of now, if you look at the strain energy, we have written as I1 bar, I2 bar, and function of J. So in this, instead of J, you use modified interpolation, and that is say J bar. So J bar is not the reduced J bar; it is you are using a modified interpolation. So that I am calling as J. Let me put tilde rather than bar, so that it is different from the other thing. So you use J tilde. So this will be as I had written for the Mooney-Rivlin model. So you will have C1 into I1 bar minus 3 plus C2 into I2 bar minus 3 plus we had K by 2 into J minus 1 square. So here use J tilde minus 1 whole square. So J tilde is a modified interpolation for J. And so maybe if it is 8-noded brick element, then you might just want to use J tilde as some constant, say A, which is a constant, and then you find out this J tilde by minimizing the difference of J, actual J, so integration over V naught, or the reference volume, and then you minimize the difference between actual J and this J tilde modified interpolation dV naught square. So you minimize this, and from this you will get then expression for J tilde, and you use this J tilde everywhere in this part, and that also eliminates the volumetric locking. And of course for the obviously if you see, finally you will find that J tilde is equal to constant for an 8-noded element will turn out to be mean value of J. So J tilde will be a mean value of J. So this is also known as mean dilatational method. So this for 8-noded brick element. So that's one way you can actually eliminate the locking. So there are others, I'm not going to discuss them. but I'm just mentioning that the one more is known as the mixed formulation. So that is based, yeah.
Sir, I had one question.
Yeah.
This J, this is generally the determinant of F, the deformation gradient matrix.
Right. Yeah.
So, sir, if we write it like that matrix, and if we find the determinant actually higher power of del u by del x and del v by del x, these kind of terms were coming.
Yeah.
So suppose if in exam you give us a problem where we have to like expand this determinant. So in that case, should we confine ourselves to first order, like should we neglect the higher order of u, delta u, or
no, in the determinant of J, it would be kind of cube of displacement gradients, as you see, because when you are looking at J is the determinant of F, which would be in terms of cube of deformation gradients. I mean, either the cube of a particular deformation gradient or product of 3 deformation gradient terms. So it would be like that. So I won't be asking you to do the expansion of that. That is used as it is, but what we are trying to do here is to eliminate the volumetric locking. We are using a modified interpolation, and I am saying that for 8-noded brick element you use J tilde as a constant. And how do we find that J tilde is by minimizing the difference between the actual J, whatever is there as it is, and this J tilde, and from there we get this J tilde. And for this case, actually it will turn out to be a mean of the J tilde would be just mean value of J over the element.
okay.
Yeah. So the third approach is mixed formulation. So in that formulation, what is done is actually J is interpolated independently. So that's an additional variable J and then we can choose the appropriate interpolation for J and solve this locking problem. So that is one. So I'm not discussing in details of this, and anybody who's interested, you can look at the actually literature. So I'm just mentioning so that you have an idea. And then fourth is also sometimes what is known as the enhanced strain interpolation. So this is also somewhat involving the mixed interpolation, but for the J we will have a different kind of interpolation. So it is somewhat similar to modified interpolation I was talking about. So it is somewhat actually similar to that. So most of the time, of course, you use the reduced integration and sometimes with hourglass control. And that's what I mean. The packages, if you look at Abacus and Sys and all these, so there would be reduced integration, and then there would be hourglass control to handle the spurious modes, spurious the zigzag pattern or the displacement. So I think this is what I wanted to discuss on this finite deformation. Now let me move on to contact mechanics. So next topic I am going to talk about is the contact mechanics. So first, the kind of to have an idea of what are the various things involved in contact mechanics, I'm going to take a simple problem and look at the solution of this problem through the different approaches which we use in the contact mechanics. So let us say the problem is just a rod under uniaxial load. So this is a rod, and then there is another rod, and that is fixed over here. And let us say that at center here there is a force F. So we discretize this rod into basically, let us say, two elements. So this is element number 1, this is element number 2, and this length is, let us say, all elements are of equal length. So this is L, this is node number 1, this is 2, this is 3, and let us say this is also L just for simplicity, and this is node number 4, and say this is node number 5, and this is element number 3, and the E into Young's modulus is EA for this also is EA, and this the gap between this node 3 and 4 is, let us say, G. So now this is a problem we want to solve. Now you would see that if F is less than a certain value, the gap might just close or it may be open. And if F is greater than that value, then there would be contact between node 3 and 4. So there are two situations possible over here. So now let's look at first the think
Hello,
of
sir.
this. Yeah.
Sir, what is actually contact mechanics? What is means definition means why we are using contact mechanics?
Yeah, so now the contact mechanics means if we have two or more surfaces which are coming in contact, so there is an interaction through the contacting surfaces. So I know there is I know there has to be some deformation compatibility and the force transfer from one surface to the other surface. So that kind of interaction we study under contact mechanics. So the interaction of two or more surfaces is studied under contact mechanics.
It's like in fracture or in crack.
Yeah, in that also it can be there. Or the other examples are, let's say, two geared T tooth are in contact, so that's a contact mechanics problem. One body is resting onto the other body, so that's also a contact problem. Here I am taking this example that node 3 and 4 may come in contact, and so there is a some compatibility in the displacement and there is some transfer of force from one body to another body. So all such problems are studied under contact mechanics. So the contact means the study of interactions of mechanical interaction of two or more bodies is defined as contact mechanics.
Okay, thank you.
Yeah. So now the first case we are looking at is the gap is, let us say, open. So then how we solve this problem if the gap is open? So now I think you already know the stiffness matrix for each element. So let me show you the assembled stiffness matrix because all the elements have same E and same L. So that can be taken out of the integration sign. And then we have this degrees of freedom. If you look at before imposing the boundary conditions, so we will have U1, U2, U3, U4 and U5, and the right hand side we will have forces. So now first if you assemble the first element defined between node 1 and 2, so yeah, we will have 1, minus 1, minus 1 and 1. That's the first element. Then second element is defined between node 2 and 3. So here plus 1, minus 1, and we will have minus 1 and 1. And then yeah, so that's I think I should write in the row corresponding to U3. So that is minus 1 and 1. So all the other elements would be 0 over here, 0, 0, 0. Yeah.
Sir, but node 3 and node 4 are same, right?
Node,
Node 3 and...
no, there is a gap between them, no?
Okay.
There is a gap between 3 and 4. So that gap
Okay.
G, you know this G, there is a gap there.
Okay, sir.
Yeah. And these elements would be 0. These elements are the matrix. Here we will have 1, minus 1, minus 1 and 1. So this is the assembled stiffness matrix. Then on the right hand side, if you look at ultimately node 1 is we are going to apply a boundary condition over there. So there would be another support reaction which we denote as at node 1. The force from node 1 will be, let's say, minus Q11. It would be in the negative x direction. So let us say this is x direction. So the force over there is going to be negative x direction. At node 2 there is a concentrated force F. At node 3 and 4 there are no forces if the gap is open. And at node 5 again there would be support reaction, so which I am denoting as this is element number node 2 and element number 3. So this is the assembled system. Now if you look at the boundary condition,
Hello.
Yeah.
Sir, if the gap is open, then how the reaction at the node 5 will produce?
Yeah, it will be 0 actually. So Q23 is going to be 0.
Okay.
but I am putting that but just to have the complete set of equations. So if you look at after imposition of boundary condition, after imposition of boundary conditions, oh, it is not writing, so some problem. So let me close this and open it again. So is the screen visible? Hello?
Yes, sir, it is visible.
Yes,
Okay. So after imposing the boundary conditions, so the boundary conditions are u1 equal to 0 and u5 equal to 0 because those are the fixed nodes. So if you impose the boundary conditions, so the final equation would be EA by L. We eliminate the first and last actually rows, so we'll get 2 minus 1 0 and minus 1 1 0 and 0 0 1. We will eliminate the first and last rows because those are corresponding to u1 equal to 0 and u5 equal to 0. So we will have u2, u3 and u4, and this will be equal to f0 0. Now if you solve this, the solution will be, you will get u2 equal to u3, that will be equal to fl upon ea, as you can see from the equations, and of course u4 will be equal to 0. So now in this we look at now the situation. Although initially we said that the gap is open, so for that now we have to see if u3 minus u4, if that is less than equal to g. Of course u4 is 0, so if u3 is less than equal to g, then the above solution is valid. Then the above solution is valid. But now the second possibility is that if u3 minus u4 is greater than g, and this means right now if we look at this fl upon ea and u4 is 0, so this is greater than g, that will imply that f is greater than eag upon l. So if f is greater than ea upon eag upon l, then the above solution will not be valid. Then the above solution is not valid. Then there is going to be interaction between node 2 and 3. So now one simple way of thinking of this problem is to solve it in 2 steps, and I will look at the problem from the different aspects. So now we can solve the problem in 2 steps. So step 1 could be that step 1 now we solve for now the same set of equations as we have written. So first is solve for u2, u3 and u4 for just f reaching to the critical value and the gap is just closing. So let us say that force is f star, which is ea into g by l, and in this the gap is just closing. So first just solve for taking the force as f star, although actual f is greater than f star. So solution, now let us say the solution for this force f star is u2 star, u3 star and u4 star. This is the solution for f star equal to eag upon l. So that's one. Then step 2, we apply the additional load and solve the problem as a contact problem. So consider additional force. Consider additional force which would be F minus F star and solve for this case and then combine the two solutions. So for this, let us say the solution is given by U2 dash, U3 dash and U4 dash. So this equation is -1 0 -1 1 0 0 0 1 and the solution is U2 dash, U3 dash and U4 dash, and this will be equal to right hand side of the force is incremental force which is F minus F star, and there would be contact force minus Fc and plus Fc. Fc is the contact force. So the contact force now, because if we are looking at the additional force, so you have of course these nodes, node 1 2 3. So there is a contact force Fc over here, and here also of course this node there is a force F which we are taking here as F minus F star, and this side also there is a Fc at node 4 and node 5. So we solve for this, but now if you look at the unknowns are U2 dash, U3 dash, U4 dash and Fc. So there are 4 unknowns. These are only 3 equations. Of course F minus F star is known because we know F star and we also know the F, so we know F minus F star. But since there are 4 unknowns, we need one more equation, and one more equation is the contact equation. So when we take the total displacement at node 3, so it would be U star plus U3 dash minus total displacement at node number 4, which would be U4 star plus U4 dash. This difference must be equal to G, because it will deform in such a way that that this difference will always remain G, because G was the gap. So now we have 4 equations and 4 unknowns. So from these 4 equations, you can solve for U2 dash, U3 dash, U4 dash and Fc. No, because now we have got this as an additional equation. So then now the total solution, if you look at that's the solution we are looking for. Then the final solution is going to be U2 would be equal to U2 star plus U2 dash, and U3 will be equal to U3 star plus U3 dash, and U4 would be equal to U4 star plus U4 dash, and this will be the final solution of the problem for any F. Now what is the alternative way? So that,
sir,
yeah,
so this gap G after that critical load F star, it will get closed, no? So it will be a very small gap.
No, that is no, but here if you look at, I am writing the total displacement U3 star plus U3 dash minus U4 star plus U4 dash, which is actually U3 minus U4. So U3 minus U4 will always be G. The difference because displacement we are measuring from the initial configuration. So the difference between the displacement of node 3 and 4 from the initial configuration is always going to be G.
Okay. So now it is closed, but from initial it will be Z only.
Okay. Yeah, initial from the initial configuration it is G.
Hello, sir.
Yeah,
sir. How sir contact force sir came, sir? Because in first case there is no contact force.
Yeah.
In second, how you approach by taking F star then F minus F star, then how it is contact force are coming? Means we are saying that the gaps are closing.
Yes, because the gap is closing, that is why the contact force is coming.
Okay, sir. So like this, then in first case also there will be some contact force because the solution is valid.
No, because there we are just saying the gap is just closing. So no, the contact force is 0. When gap is just closing, then the contact force is going to be 0. But when F is more than F star, then contact force would develop.
Okay, sir.
Yeah.
Then here F is greater than F star.
Yeah, F is greater than F star. Yeah.
Okay. Sir, in the first case also we are applying F.
Yeah, we are applying F, but that I just said first. Initially I said gap is open, so there is obviously F is less than equal to F star.
No, sir. In A, if U3 minus U4 less than G, that case I am saying. Means if the second case is not valid, then we will approach this process, this method. If U3 minus U4 is greater than G.
Yeah.
Then I am saying U3 minus U4 less than G. If U3 minus, then there will be contact force.
No, it will not be, no, because U3 minus U4 is less than G. So node 3 is not coming in contact with node 4. Or it may be with when equality sign holds, it will be just touching. So the force would still be, contact force would still be 0.
Then U3 minus U4 is greater than G, then there is contact.
Yeah, then there would be contact force would be developing between the node 3 and 4.
So actually, physically, I can understand how U3 minus U4 is greater than G is while there is contact force.
G means U3 is more, U4 is less. And it is such a way that this difference is greater than G. So then the contact basically gets established.
Okay.
Yeah.
Okay.
So now, there is now this solution is in 2 steps. So we can also do the solution in a single step for this case if F is greater than F star. So there is an alternative solution for when F is greater than F star. So the situation is the same. The what I have listed over here, what I have drawn here. So if you look at now the conditions, so the element level stiffness matrix is same, EA by L 2 minus 1 0 minus 1 1 0 0 0 1, and U2 U3 U4 are the total solution. On the right hand side you will have total force minus the contact force, and here plus the contact force, because here it is in negative x direction and here it is in the positive x direction. So now here you have this F is a total F, as I already said. Of course F is greater than F star, and the other condition is that U3 minus U4 should be equal to G, or U3 minus U4 minus G is equal to 0. So what you can do now, if you look at this, so now we have 4 equations and 4 unknowns. Unknowns are U2, U3, U4 and FC, and the equations are these 3 equations, and this is an additional equation. So now if you want, you can write U4 is equal to U3 minus G from this equation. And then if you look at the last equation, the last equation from here, the third equation from the first set of 3 equations, we can write that is EA by L into U4 is equal to FC. And U4, of course, you can write in terms of U3 and G. So it would be U3 minus G is equal to FC. And then you can actually put this in the first 2 equations. So now the first 2 equations, if you look at the first 2 equations, so they will become EA by L and 2 minus 1 and 1, and then we have U2 and U3, and this side we have this F, and now FC is minus FC, so minus FC is minus EA by L into U3 minus G. I think you're following. This is straightforward. So we are substituting in the first 2 equations. The first equations can be written like this. Now what you can do is this minus EA into U3 by L. U3 is an unknown, so this can be taken to the left hand side. So you can write this equation as EA by L 2 minus 1, and here at this diagonal this term would be added. The right hand side it is minus. When we take it to the left hand side, it would become plus. So here we will have 2, and then you will have U2 U3 is equal to right side we will have F, and this minus EA by L into minus G will be EA G upon L. So this will be the additional term. And then you simply solve for U2 and U3. And once you solve for U2 and U3, then you can get the U4 from this equation. Once U4 and U3 are known, U3 is known, you can get then U4. So this will be the total solution. Now we want to look at something more. So this is of course one, know that these are different alternatives we can use to solve the problem. If same contact problem can be stated in terms of minimization of potential energy subject to certain constraint. So the same problem where F is greater than F star, and for that we want to solve this problem. So the problem can also be written as, so I'm directly writing, although you can go through the element wise also. So here I'm saying minimize I, which is the total potential energy functional. So after imposing the boundary condition, we are writing the total potential energy functional, which is the strain energy plus the load potential of the forces. So this you can write it as U2, U3, U4. So that is U transport. Yes, any question?
Yes, sir. Sir, can you please explain how we know the G value in this last?
G will be given. So we have to know that initially in the undeformed configuration, what is the gap between those two nodes. So G has to be a given parameter, like L is given, E is given, A is given, F is given. G also has to be a given known parameter.
Okay, sir. Okay.
So this is 2 minus 1 0 minus 1 1 0 and 0 0 1 into U2 U3 U4. So this is the it is like D transpose K into half of D transpose K into D. That's the total strain energy, and minus the potential of external forces. So that would be U2 U3 U4 transpose into F00. And so this will be, now we are talking of a case where F is greater than F star. So then U3 minus U4 has to be equal to 0. So if you know for sure sort that, so this has to be subject to U3 minus U4 minus G equal to 0. Now how do we solve this problem? So this is minimize this subject to this constraint. So as you see, it's a optimization problem, a minimization problem. So for solving this minimization problem, there are two different approaches. Now you would have learned somewhere Lagrange multiplier method and penalty method. So I'm going to discuss both of these. So that's the another way of looking at the solution of this problem. So say a Lagrange multiplier method. So now in the Lagrange multiplier method, what we do is, right now we have no minimize this subject to this constraint. So we combine these two in the sort of a modified total potential energy functional. So we call it as construct a modified total potential energy functional. Let us say we denote that by I dash. So I dash would be equal to I plus Lagrange multiplier lambda times the constant U3 minus U4 minus G. So here no lambda is a Lagrange multiplier. And that is also an unknown. So we are introducing an additional unknown in the form of Lagrange multiplier. And now for equilibrium, then delta I, the variation of I dash has to be 0. So for equilibrium, delta I dash, which will be equal to delta I plus the variation of this additional term which we have added. So since lambda is also an unknown, so we take its variation. So delta lambda into u3 minus u4 minus g will be there, and plus lambda into the variation of other terms. So delta u3 minus delta u4, and this must be equal to actually 0 for the equilibrium of the system. So now if you look at these equations, now if you look at the delta I, you already know how to take delta I. For the second part I have already written, and the delta I for the first part over here, what you have is half will go, and then you will have delta of u2 u3 u4 transpose EA by L, and this whole stiffness matrix into u2 u3 u4, and this side delta of u2 u3 u4 transpose f0 0, and then we equate the coefficient of delta of u2 u3 u4 equal to a null vector, and we get the equations. So you know this. From here the equation will come as, say, EA by L, and you will have delta of u2 delta of u3 delta of u4 transpose, and then here you are going to have 2 minus 1 0 minus 1 1 0 and 0 0 1. So that's the same thing. Into you will have u2 u3 u4. Now the same equation, and is equal to right hand side we will have. So if we take delta u2 delta u3 and delta u4 transpose, and now you see delta u3 and u4 have got this lambda term. So we will have f minus lambda and plus lambda when you take to the right hand side, and plus of course we will have this delta lambda. We still have delta lambda into u3 minus u4 minus g equal to 0. The whole thing is equal to 0. So from this the equations you are going to get, first equation set of equations is EA by L, and then 2 minus 1 0 minus 1 1 0 0 0 1, that's the stiffness, into u2 u3 u4 is equal to right hand side we will have f minus lambda and lambda, and the other equation is the coefficient of delta lambda also should be separately 0, so that will give u3 minus u4 minus g equal to 0. So now here you would see the interpretation of Lagrange multiplier. Now if you compare this with what we wrote over here, this equation, so you see lambda is just like a contact force. As you see here, minus lambda and here plus lambda we are getting, so it is identical to that. So we can say that the Lagrange multiplier can be interpreted, lambda can be interpreted as contact force. That is, you can say lambda is nothing but actually FC. So now if you combine all the equations together, although you can keep the equations in this form, these are the three equations, this is the fourth equation, number of unknowns are u2, u3, u4 and lambda, and you solve for these four unknowns using these four equations. If you want, you can also put all the four equations together, that is also possible. So you can write it as, now I'm taking EA by L inside, so 2 EA by L minus EA by L, and then you have 0 0 minus CA by L, because I want to take the unknowns u2, u3, u4 and lambda. So EA by L, then we have this EA by L 0 and 1. When I write the whole thing you would be clear about it. EA by L, and then minus 1, and then 0 minus 1, this is plus 1. Now all the four equations you are putting together, then the unknown vector is u2, u3, u4 and lambda. So all the four equations we are putting together, and the right side we will have f 0 0 and g. That is, the last one is actually this equation, and first three are these equations. So now of course these are the four equations and four unknowns. So what you can do is you can solve these 4 equations solve for u2, u3, u4 and lambda, and that will be the solution for f greater than f star. That's what we said. So one is using the Lagrange multiplier approach. The other one, no, there is another method also. You can actually use the penalty method. So in this Lagrange multiplier method, number of unknown has increased by 1. That is, Lagrange multiplier itself is a unknown variable. So number of unknowns are increasing. So if there are this kind of more constraints are there, there will be more number of Lagrange multipliers. So we have another method known as the penalty method. So in the penalty method, what we do is similar to Lagrange multiplier approach, we construct a modified total potential energy functional, but using the penalty term. So the constraint is incorporated through a penalty term. So construct a modified total potential energy functional So now let me also denote this also by I dash, although I dash of Lagrange multiplier is different from this. So I plus, now we use a penalty term. So Kp is the penalty stiffness, U3 minus U4 minus G, and we do a whole square. And the reason is we are adding this additional term. So if this constant U3 minus U4 minus G equal to 0 is violated, so this square will make sure that it is taken care in both positive and negative values of U3 minus U4 minus G, and then we multiplied by a large number Kp, so that a small violation of the constraint will be reflected in the this modified total potential energy functional, so that the constraint will not be actually violated. And here this, what is this Kp? So Kp is known as penalty parameter, or sometimes we call it as penalty stiffness, penalty parameter, which is and use this penalty parameter has to be a large number to enforce the constraint accurately, which is a large number. So large, how large is compared to the this stiffness, we have the other stiffness terms. So we have EA by L is the representative stiffness, so it should be at least 1000 times of EA by L. So that is the order of this penalty parameter, so which is a large number. So now if you once you have this I dash, so you know the for equilibrium delta of I dash should be equal to 0, which would be delta I. Now Kp is a known parameter. In the Lagrange multiplier, lambda is an unknown, so its variation is also taken, but here Kp we are taking a priori specified known number, so there is no variation of Kp. So we will have Kp into the variation of other term, so half will go, and then you will get U3 minus U4 minus G into the variation of the same. So delta U3 minus delta U4, and this is equal to 0. So from this, now you can now let me write directly the equation. You can do the way we did for the Lagrange multiplier. So from this you will be able to generate the equation, which will be in this form: 2EA by L minus EA by L. You can take the variation the way we did for the Lagrange multiplier, and then you can write the final set of equations. So it will be 0, and then we will have minus EA by L, and here we will have EA by L. Now see this with U3, this Kp is getting added, so here we will have plus Kp, and with U4 it is minus Kp, so here we will have minus Kp in the third row, and here 0, and then in the second equation you are going to have with this minus delta U4, so that will give you minus Kp here, and then here it would be EA by L plus Kp, and then you have U2, U3, U4 is equal to, right hand side we are going to get F, and then this with G, delta U3 G will go to the right hand side, and delta U4 G will also go to the right hand side. So we will have Kp into G and minus Kp into G. So now your the advantage is, although we have to use Kp as a large number, so but now we will be solving only these 3 equations for U2, U3, U4 with Kp as a large number. So although the problem sometimes if we take Kp value very large, so then yield conditioning of the stiffness matrix might take place, and then you won't be able to solve for it. So usually, as I said, we take 1000 time of the maximum diagonal stiffness in the water is coming from the normal integral functional. So solve for U2, U3 and U4. So I think from here to here, you can do similar to what I have done for the Lagrange multiplier. So you try to rearrange, take the coefficients of delta U2, delta U3, delta U4. You will get these three equations, and then you can solve for this U2. So this is in this manner. And now, yeah. So now see, so far we are solving the problem actually in two parts. One is for f is less than equal to f star, and another is f is greater than f star. Now if we want to combine these, so now that's the next level. Next level, you can see we can combine the two situations together. So then the constraint would be replaced by an inequality constraint. So the problem statement for both cases, problem statement for both cases, that is, one is f is less than equal to f star and the other is f is greater than f star. So for these two we can put the problem together. So how do we write in that case? Let me again write it as the minimization problem. So because we are going to write the total potential energy, we are going to minimize subject to the inequality constraint. So this problem again can be stated as minimize this total potential energy functional I, which is half of U2, U3, U4 transpose into yeah, A by L you can take outside. So 2 minus 1 0 and minus 1 1 0 0 0 1 into U2, U3, U4 minus we will have U2, U3, U4 transpose into force vector F0 0. This is subject to now the constraint we are putting both together. So then we can write this constraint as subject to U3 minus U4 minus G less than equal to 0. So either U3 minus U4 minus G is less than 0 when the contact is open, and when contact is just closed, U3 minus U4 minus G will be equal to 0. So these are the conditions. The two possible conditions are combined into one. So then the problem statement is basically the single statement. The two cases, all the possibilities are combined into a single problem statement. Now if you want to solve this minimization problem, so I don't know how many of you have done a basic course on optimization. So you would have done, if you have done the course on optimization, you would have learned how to use Lagrange multiplier approach for solving a optimization problem with inequality constraints. So I'm going to list how we do it. So what we do is, when we want to use this Lagrange multiplier approach, so in the Lagrange multiplier approach, what we do is, again we construct the modified total potential energy functional, which would be I and plus Lagrange multiplier lambda times, but we convert this inequality constraint into an equality constraint by introducing a slack variable. So that slack variable is, let us say, s square, so that it is always a positive number. S square is a positive number. So you have U3 minus U4 minus G. Because it is less than equal to 0, so we introduce a slack variable. So with this it becomes plus s square is equal to 0, and then we add this as a Lagrange multiplier in equality constraints. So here s square is a slack variable. So now when you take the now for the equilibrium, obviously the delta I dash has to be equal to 0. So delta I dash would be equal to delta I plus of course as we know that Lagrange multiplier is an unknown, so we will have one term is delta lambda and u3 minus u4 minus g plus s square, and plus we will have lambda times the variation of other terms, so delta u3 minus delta u4, and plus we will have this basically the s, so s is also an unknown, so we will have 2s into delta s, and this whole thing is equal to actually 0. So this is how now you set up the equation based on the Lagrange multiplier approach. So you will see that now from this, if we want to get back our equations, so we will have EA by L. Now again, no, you take the variation, take delta of U2, U3, U4 and delta lambda coefficient of that equal to 0, you get these equations. So you get 2 minus 1, 0, minus 1, 1, 0, 0, 0, 1. And then you have U2, U3 and U4 is equal to, now the first three equations would be like f minus lambda plus lambda. Then another equation would be u3 minus u4 minus g plus s square equal to 0, because this will come from the coefficient of delta lambda, and additional thing will come from this coefficient of delta s should also be equal to 0. So that gives you the lambda into s is equal to 0. And the additional thing is that lambda has to be greater than equal to 0. The contact force Fc, because lambda is interpreted as contact force, so this lambda has to be greater than equal to 0. And then you solve these equations, and after solving these equations you get the solution of the problem. So that's the one way of looking at this. The same inequality constraint can be handled using penalty method also, but the application of the penalty method is different for the equality constraints and inequality constraint. So now from the same thing, and see these we are going to discuss when we have the general surfaces are in contact, so these techniques would be extended to those problems. So in a penalty method, if we want to solve this problem, we will construct I dash is equal to I plus Kp by 2, again similar to what we did for the separate equality problem, where we said that let us solve separately for f greater than f star. So now here what we want to add is, if u3 minus u4 minus g, if this is actually less than 0, then the constraint is satisfied, we need not add any penalty term. But u3 minus u4 minus g, if it is greater than 0, so then that is violation of the constraint, and then the corresponding penalty term should be added. So for that what we do, we take the maximum of basically u3 minus u4 minus g and 0. So we take the maximum of actually these two, and then take its square and multiply over here. So this is when we are handling inequality constraint. So this is one way of handling the inequality constraint. As I said already, if u3 minus u4 minus g is less than equal to 0, then there is no penalty added in I, total potential energy functional. But if u3 minus u4 minus g is greater than 0, so then the inequality constraint is violated. So for that, then we add a penalty term over here. So we write this equation like this. And then for equilibrium, delta I dash should be equal to 0, which would be basically equal to delta I plus Kp. Now Kp is a known penalty parameter. So we will have here maximum of, then of course, u3 minus u4 minus g and 0. So this term, and of course u2, u3 are unknown, so their variation will come delta u2 minus delta u3. Sorry, delta u3 minus delta u4. Equal to 0. So now from this, if you look at the equations which have to be solved finally will be 2EA by L minus EA by L 0, and then minus EA by L 0, 0, 0, EA by L. Penalty terms I am keeping on the actually the other side separately. So that is u2, u3 and u4. same set of equation plus now the penalty terms I am keeping separately here, so 0, and then we will have Kp into maximum of u3 minus u4 minus g and 0, whatever is maximum, and then we will have minus Kp and then the maximum of u3 minus u4 minus g comma 0, and this is equal to f00. So the problem will be actually known once we have calculated f star. So we would already know that whether u3 minus u4 minus g is actually less than 0, then the penalty terms are going to be 0. And if we know the u3 minus u4 minus g is coming greater than 0 from the assuming that and the gap is open, so then actually gap is closing, and then you have to add this penalty term and solve the problem. So this is how you will solve the problem. So these are the few typical, you would see, we have seen a very simple way of solving the problem. Then we have introduced the minimization of the total potential energy functional with a constraint, then Lagrange multiplier penalty approach, then posing the problem, both the cases, f is less than equal to f star and f greater than f star into a single problem. And then we have seen how the Lagrange multiplier method or penalty method are used to solve this problem. So I think this is where I want to stop, and I will just give you another problem you try, although I will discuss also this in the next class. So the example 2 is a problem on beams, the contact problem. So let us say we have a beam and this is subjected to a distributed transverse load, uniformly distributed load, let us say that is Q, and this is X coordinate and this is Y coordinate. So these are the nodes. This is node 1. Discretize this beam only into 2 elements, and say length of the element is actually L, and its flexural rigidity is EI, and this is Q. Then this is node 2, and then this node 2 comes in, actually below that there is a spring. This spring is there, the one end of this spring is fixed. So let us say this is node 3, and the stiffness of the spring is, let us say, K, and initially the gap between node this and this gap is, let us say, G. So try to look at know the solution of this problem using the same steps which we have done for the truss this rod problem. So you also try to do this problem using the this particular problem, using all the steps. First solving the problem into 2 steps, assuming that gap is open, then solve the problem, then identify the critical value of Q equal to Q star, below which there is the contact is open, and above which when the Q is greater than Q star, the contact between 2 and 3 is closed, and like that you solve the problem. Then pose it as a minimization of the total potential energy subject to the equality constraint, and then bring in the both the cases together and bring in inequality constraint, and then try to apply Lagrange multiplier method and the penalty method. So I think this is where I want to stop, and if you have any doubts and questions, you can ask. Yeah, so are there any doubts, questions?
Hello, sir.
Yeah.
Sir, like I was asking about this gap, sir, if we consider any like real scenario where we don't know what will be that initial gap will be, like we are given some 2 system.
Yeah.
So how do we find that gap, initial gap?
So then that gap has to be calculated from the geometry. So I think we are going to look at that also. So when we are when I will discuss the general problems, I will discuss how to calculate this gap. But as of now, we are assuming that this gap is known. So from the initial configuration of the system, the gap at every node has to be known. And that can come from the geometry of the system, the 2 systems coming in contact.
Okay, sir.
Yeah. So are there any other question, anybody? Any other question? Please try to solve this example 2 using the same steps. I will be discussing it, but it would be better if you solve, so then you will know know where you have doubts and where you have not understood the steps or what are the difficulties, or you will appreciate the concept. So are there any other question? Anybody has any other question? Doubt? Okay, so if there are no questions and doubts, I'm stopping. Thank you all for your attention.